This is video 2 of topic 5 on infiltration. This video covers the soil-water flow. Gravity and soil water pressure gradients drive flow. It's conventional to measure pressure relative to atmospheric pressure, which we know from previous courses is called gauge pressure. In saturated flows, the pressure is greater than zero. It increases as we move downwards in the saturated zone. In unsaturated flows, something more interesting happens, which is that the pressure is actually less than atmospheric pressure, less than gauge pressure. The water table is then the surface where the pressure is equal to zero. Negative pressure, which occurs again in that unsaturated region, is called tension or suction, and so it actually pulls water into this layer. Pressure head, or psi, can be defined as psi is equal to P over gamma W, where gamma W is rho Wg, or the specific weight of water. Remember, we've seen this term before in Bernoulli's equation. We have pressure head, velocity head, and elevation head. It's the same idea here, and so the units are going to be in length or meters. Pressure head, or psi, is also called tension head, matrix potential, matrix suction, or capillary suction when the pressure is less than gauge pressure. And like pressure, the pressure head is less than zero in the unsaturated zone. So all of these values are going to be negative values in the unsaturated zone. We can map out this relationship between water content and pressure head through something called the moisture characteristic curve. Again, this shows the relationship between pressure head, here, and water content, or theta, here on the bottom axis. And the curve that we're looking at is this red one. There are a few important points here. Pressure head is equal to zero when the water content is equal to the porosity. In other words, when the soil is fully saturated. As we begin to increase the pressure head, the water content changes very little as the tension increases to this inflection point here, which is called psi AE, or the air entry tension. Okay, so very little change here in the water content, but then something interesting happens beyond this air entry tension. As the tension increases beyond the air entry value, the water content then decreases rapidly, and then more gradually up towards the top here, at which point there's a sort of asymptote. Okay, and note that the curve shape is going to be slightly different for different soil types. This is just one of many possible curves. Hydraulic conductivity is another important characteristic, and it's the rate or volume per unit time per unit area at which water moves through a porous medium under a unit potential energy gradient. That's a sort of difficult technical definition, so put more simply, the hydraulic conductivity measures how easily fluid, usually water, can move through pore spaces or fractures. And the rate is determined mainly by the size or cross-sectional area of the pathways that are available for water movement. Under saturated conditions, the situation is fairly simple. The pathway size is determined by the soil grain size. In unsaturated flows, it's a little bit more complicated. Here, the rate depends on the grain size as before, but also on the degree of saturation. And this gives us our second curve here, which is for hydraulic conductivity. Again, there are some important points on this graph. So the first is, for a given soil, KH is very low, you can see here, very low, at low to moderate water contents, and this is because the water just begins to coat the soil grains. It doesn't actually flow through the soil, it coats the grains. These are for unsaturated conditions. Then KH increases non-linearly to a saturated value, KH star, as the pore spaces fill and the water content increases to saturation, which again is here. Importantly, the hydraulic conductivity depends on both the soil grain size and the degree of saturation, as we just saw. And so this figure here compares the relationship between K, H, and S for a few different soils. The first thing you should note is as we move from clay, for example, to a sandy loam, we get faster and faster flow. This is a log scale here, so log base 10. And this is the degree of saturation, which is the water content over the porosity. Okay, and we get faster flow as we get more towards saturation. Note too that these are orders of magnitude difference, because again, it's a log scale. We've looked at some theoretical information. Now let's look at water conditions in natural soils. Imagine that a soil is saturated, and then it's allowed to drain. Possibly slowly, possibly quickly. This occurs without evaporation, without plant uptake, and without capillary rise. We can imagine that as it drains, its water content decreases indefinitely in a quasi-exponential fashion. So much faster when the water content is higher, and as it begins to dry out, its water content decreases more slowly. The drainage rate will also decline exponentially, and after a few days it probably becomes negligible. Particularly if you imagine adding water to sand or gravel. You can imagine how even after an hour there's going to be basically no drainage. With clay it will take a lot longer, for example. We can define a characteristic called the field capacity, or theta FC, as the water content below which drainage becomes basically negligible. And the field capacity is then essentially an index of the water content that can be held in the soil against the force of gravity. For sands, theta FC might be about 0.1, and for clays it might be higher, so up to about 0.3, for example. If you want to see how this works in practice, you can try this experiment at home at this YouTube site, or another one here, which is a very similar experiment. Here's an example of what this drainage looks like. Here we have a loamy sand. You can see it drains much more quickly. Here's a clay loam. It drains more slowly. This value up here is the original water content, so it's fully saturated here, and then it drains down to the field capacity here. And similarly here for loamy sand, this is its field capacity around a water content of 0.1. And here you can see the number of days. In nature, water is removed from a soil that's reached field capacity principally by direct evaporation or by plant uptake as part of the process of transpiration. However, we know that plants cannot exert suction stronger than a certain level, and when the water content is reduced to that point, then transpiration ceases and plants will begin to wilt. This point is called the permanent wilting point, or theta permanent wilting point, PWP. The water that's available to plants then for growth is called the available water content, or theta A, which is the difference between the field capacity and the permanent wilting point. And if you want to review these definitions further, here's a nice video. You can also see a number of experiments showing how soils behave with water from this excellent video here from the University of Liège. This is a figure of the concepts that we've just discussed. So here's the saturation point, here's the field capacity, here's the permanent wilting point. And notice that this is again a sort of log scale here of pressure head. Okay, so in centimeters of water, and you can see it rises very quickly. Again, it's a log-based scale, so 15,000, 31,000, a million, and so on. And here's a number of figures that show what the permanent wilting point looks like, as well as hygroscopic water, which is just the water that's coating the grains. Here's where you have gravitational water draining, and here's field capacity. Another figure showing the same information is here with soil saturation, so no air content. Then field capacity has mostly water, but also some air. And then the permanent wilting point, which is mostly air and very little water. This one isn't, of course, completely accurate because the water actually coats the grains rather than filling pores. Okay, and this is the end of video 2.